Hey guys, my name is Dan Heinzel, and I will be talking to you a little bit about the interpreter design pattern. In this presentation, I'll cover several different aspects of it. We'll talk about the classification, the intent, motivation, structure, consequences, known uses, and at the end, I'll give you a short demo that shows its utilization in code. The interpreter design pattern is classified as a behavioral pattern. And that means that common communication patterns between objects are identified and recognized by this type of pattern. And the specific intent of the interpreter design pattern is, given a language, define a representation for its grammar along with an interpreter that uses the representation to interpret sentences in the language. The motivation of this is if a problem is frequently occurring, it may be worthwhile to express instances of the problem as sentences in an easily recognizable language, something a little more human-oriented. And an interpreter is used to translate the problem into sentences. So before we get into the structure of it, I'll talk to you a little bit about a real-world example of an interpreter. Musicians act as an interpreter. Music notation, if you're not familiar with it, is the language of music. The sound and the pitch and duration can be represented by a series of symbols. And if you're unfamiliar with music script, the shape of the note, the stem, and the amount of flags on it represents its duration. And its position, according to the lines, represents the pitch of the note. So this note, for instance, is a different pitch as these ones because they lie in different spots of the line. Musicians reproduce the original pitch and duration represented by the sheet music by reading and interpreting it. Here's a quick class diagram of what this means. So you have your musician right here, which is the keyboard, and this right here is the output sound, and this right here is the music script. And in this example, the music notation is an abstract expression composed of notes and signatures. The structure of the interpreter design pattern is tree-like, and it follows several rules. Its structure consists of terminal nodes and composite nodes. A terminal is the leaf node on the structure, when the composite is the subtree. And this type of pattern relies on recursion for the traversal. So this is a generic example of it. You have your context, client, abstract expression, terminal expression, and non-terminal expression. Your client, context, terminal, and non-terminal expression are all concrete. And the abstraction occurs in the abstract expression. So if you look at this, your client is speaking to the context and the abstract expression. And the terminal expression terminates right here, and the non-terminal recursively creates more and expands the tree. So let's look at this expanded a little bit. You have your expression right here, and in this instance we're going to be talking about the phrase raining cats or dogs. And so raining right here is your terminal expression, and cats or dogs is your composite. It can be either or. And so when you go down the tree, you have a little bit of your recursion right here that produces two terminal nodes. You have cats or dogs. And this is a little bit about what the tree would look like if it were expanding. And each subclass of the above expression implements the interpreter to match the next part of the input string. So there are a few consequences to using this pattern. It is easy to change and extend the grammar. You can do this by using inheritance, or you can build it incrementally. Unfortunately, complex grammars are very, very costly and difficult to maintain. The interpreter needs at least one class for each rule in the grammar, and the greater the number of classes and variation makes it difficult to use the pattern. And when it comes to the interpreter needing at least one class, I'll show you an example of that in the code. So the usage of this: when should an interpreter pattern be used? It should be used when time and efficiency are not a huge concern due to its slow implementation nature. The code interpreted is not complex, so it's very simple and straightforward, and you can easily build it. And you should also use it when an application requires different types of output to be produced. And the best known usage is a report generator, something that might generate a report in several different styles and layouts. So I'll show you a quick application example. This right here shows, it's just a basic conversion thing between units of measurement. So for this, I'll write 2 miles to kilometers. And this is your input, and this is the language that I have created for this example. And it'll convert it to its appropriate output. So let's see what 2 miles converted to kilometers equals. So 2 miles equals 3.218 kilometers. Okay. So here's the implementation steps. Step 1, you want to define the layout of the input. And for this one, I decided to make the layout your input number, which is going to be your quantity, your initial measurement, which is the units that you're going to choose, the word to, that's static, and your desired measurement unit. So in the program, I'll step through and debug this so you can see what's happening step by step. So we'll run this, 2 miles to kilometers. It's going to accept the input string, and right here it stops. This is where it's actually retrieving the data and it's parsing it to its appropriate form. When you step through it, it's going to take all of the input on it after it declares everything. It's going to take all the input and split it into an array of strings, which will each represent one component of the language that I've created. And right here, your conversion response is just it's kind of prepping the response to be sent back. So we'll continue this. And so right here, this is where it's actually using the expression that I've created. In this situation, since we're converting miles to kilometers, we have this right here where the initial expression is miles. So these are the different attributes of it, and it calls the appropriate functions based on what is being used. So we'll continue. And it goes through, and this is where it's actually doing the parsing of it, this area. All of these methods are parsing it and preparing the output string to be created. This one in particular is the output string. So when it does all of its parsing, it's going to continue it and parse it into a recognizable language, and that is the result of this. So let's talk about the different classes. You have right here, this is your main structure, your client, which is going to be a concrete function, and it will contain just whatever you decide to put into it. Right here, your conversion context is also another concrete method, and this is just kind of, in this situation, it's more of setters from the initial main method. And all of these right here are concrete classes, and these represent what I was talking about earlier regarding the multiple classes for each thing. So in this situation, you have miles, which 1 mile equals 1 mile, 1 mile equals 1.609 kilometers, and etc. Each time you add a new measurement in, you have to go in and you have to add an entire new class to compensate for it. And as far as the actual abstraction of it goes, we have the expression right here. This is the public abstract class that contains all of the abstract methods to this. So I defined the layout of this. I showed you a little bit of that. You create the parse tree, which is going to be those various classes that I showed you, and then you output the result, all shown within the code. And these are some of the references that I used when creating this presentation. Thank you. If you have any questions or anything, you can email me at dheinz@umich.edu.